Welcome back everyone for another SVSU Math and Physics Resource Center tutoring video. My name is Brendon, I'm going to be your tutor, and we're going to go back into the ratio test for this video, except this one we're going to show how we can use it to show a series converges in contrast to how we showed it diverged in the last video. Alright, let's get into it. Alright, ratio test part 2. So we're going to get into another example using the ratio test, but first let's kind of recap what the ratio test is. So we have a series from n is equal to k to infinity, where k is just a constant, of a of n, which is just a function of n. And then we're going to take the limit as n approaches infinity of the absolute value of a of n plus 1 divided by a of n. And if we get that equal to some constant L, then we can use these criteria to see whether our series converges or diverges. So if L is greater than 1, our series diverges. If L is less than 1, our series converges absolutely. And if L is equal to 1, then this test is inconclusive, and we need to use another test to check to see if it converges or not. So let's go ahead and get into this example. So first thing I'm going to do is I'm going to identify my piece. So this is a of n. And let's go ahead and write out the a of n plus 1 term. So I'm just going to plug in n plus 1 everywhere I see an n. So it's going to be n plus 1 on the numerator. Then I have a 3n plus 1 minus 2 factorial. Okay, so then we want to simplify this. So this is going to be equal to n plus 1. And then I can distribute that 3 through. So it's going to be 3n plus 3 minus 2 factorial. And then we want to simplify this one more step. So it's going to be n plus 1 all over 3n, looks like plus 1 factorial. Okay, so now that we have our a of n plus 1 term, let's go ahead and plug everything into our limit. So this is going to be the limit as n approaches infinity. Looks like, so the absolute value, I'm going to write my a of n plus 1 term first. So it's going to be n plus 1 divided by 3n plus 1 factorial, divided by my a of n term, which is just going to be n over 3n minus 2 factorial, and then the absolute value bar. Okay, so just like in the last video, we're going to go ahead and use our keep switch flip method for a double fraction, and then so that's going to keep the numerator, switch the sign from division to multiplication, and flip the denominator. So let's see what that looks like. Limit as n approaches infinity of the absolute value of n plus 1 over 3n plus 1 factorial multiplied by, so now we're going to flip the denominator, so 3n minus 2 factorial divided by n. Okay, so off to the side, I'm going to go ahead and do the factorials out. So factorial is just going to be 3n minus 2 multiplied by, then we lower by 1 every term. So it's just going to be 3n minus 2 minus 1, so 3n minus 3 times 3n minus 4, and so on. Okay, so now let's do the one that's in the denominator. So we're going to start with 3n plus 1. Then our next term is going to be 3n plus 1 minus 1, so just 3n. And then 3n minus 1. And then 3n minus 2, and dot, dot, dot. Okay, so if we see, I have a 3n minus 2 term that's going to cancel with this 3n minus 2 term, and then all of these terms to the right are going to cancel with all of these terms to the right in the denominator. So then that's just going to leave us with these 3 terms that are in the denominator. So let's go ahead and simplify this. So this is going to be the limit as n approaches infinity of absolute value. It looks like I have n plus 1 in the numerator, and then in the denominator, I have whatever pieces are left from my factorial, so that's these 3. So it's going to be a 3n plus 1, a 3n, and a 3n minus 1. Okay, and then I still have this n left over as well from the denominator. Okay, so now let's go ahead and evaluate this limit. So for this limit, what I'm going to do is I'm just going to look at the powers of the numerator and the powers of the denominator. So in the denominator, I have 4 pieces here that are all being multiplied, and each piece has an n in it. So then that tells me that my highest power in the denominator is going to be n to the fourth. And then my highest power in the numerator here is just from this n, which is n to the first. So that tells me that when I plug in my infinity for n, my n to the fourth is going to get much bigger, much faster than my n to the first in the numerator. So that means I have an infinity in the denominator, which means my limit is going to approach 0. Okay, so let's go ahead and take a look at what this means. So if we go back up to our criteria, if L is greater than 1, the series diverges. Well, we don't have that because 0 is not greater than 1. If L is less than 1, the series is going to converge absolutely. So this is the one that we have because 0 is less than 1. So then that tells us that this series converges. Okay, and so that was just another example of the ratio test. And so in the next video, we're going to get into the last criteria where L is going to be equal to 1, and then we're going to hopefully show what we can do when this does happen. All right, thanks for watching this video.